A silent alert ripples through mission control. As the interstellar visitor 3I Atlas skims past Mars, NASA's public channels tighten, rumours flare, and telescopes across the solar system pivot toward a once-in-a-generation target. Tonight, we separate signal from noise, what 3I Atlas really is, what Mars is about to see, and why the world thinks NASA went dark. It began as a faint, moving smudge in a Chilean sky. 4 specks of light nudged across successive frames from the ATLAS survey telescope at Rio Hurtado on July 1st, 2025. Astronomers ran the numbers, extended the track with pre-discovery images, and the orbit solution refused to close. The path was hyperbolic, an open curve that doesn't loop back to the sun. In plainer terms, this thing was not born here. That's why the designation reads the way it does. 3I Atlas, the 3 marking only the 3rd confirmed interstellar visitor, the I for interstellar, and ATLAS honouring the survey that first rang the bell. Calling it interstellar isn't a hunch, it's orbital mechanics. If you trace its motion backward, the comet comes at us too fast to be captured by the sun's gravity. Early in July, its speed relative to the sun was already on the order of 137,000 miles per hour, about 61 kilometers per second, and it's been accelerating as it drops inward. You can picture it like a rock skipping through the solar system's gravitational well. One steep dive, then gone. That's the telltale signature of an object that formed around another star, wandered the dark between systems for ages, and just happened to slice through our neighbourhood this year. It's not a bare chunk of rock. Telescopes show it's active, venting volatiles that sunlight boils off, so astronomers classify it as a comet rather than an asteroid. The activity throws up a coma, a gauzy halo of dust and gas that hides the true core and makes size tricky to pin down. Even so, Hubble's early measurements bracket the nucleus between roughly 440 metres and 5.6 kilometres across. Far from planet killer scale, but hefty enough to study in detail, especially compared with our last 2 visitors. 1I/Oumuamua, no visible coma, very odd, and 2I/Borisov, a classic-looking icy body. This one looks and behaves like a comet, just from somewhere else. From the start, planetary defence folks made one point absolutely clear: it's not coming near us. The closest it gets to Earth is about 1.8 astronomical units, around 170 million miles, 270 million kilometres, so there's no danger scenario to spin here, no hidden threat. Instead, the story is opportunity. An object built under another sun is giving us a clean laboratory test of our ideas about comet chemistry and dust, and how those ingredients compare with the ones we know. It's like finding a sealed sample jar from a different kitchen, drifting through your pantry. Before it fades, we also get a front row checkpoint at Mars. On October the 3rd, 2025, 3I Atlas sweeps past the red planet at about 18 million miles, 29 million kilometres, moving close to 193,000 miles per hour. That geometry is perfect for a solar system stakeout. Orbiters and rovers already circling or parked on Mars can try to watch the visitor go by from a vantage point we almost never get. The fleeting alignment turns Mars into an outpost observatory for an interstellar comet, a sentence that would have sounded like science fiction a decade ago. Naming quirks aside, the ATLAS tag carries a quiet poetry. The survey's job is to notice the unassuming, to transform routine sky patrols into messages about what's out there. Within hours of those first detections, follow-ups and recovery images extended the arc, tightened the orbit and locked in the verdict: hyperbolic extrasolar, a one-way ticket through our sun's domain. The same NASA page that lays out the basics also lines up a who's who of instruments: Hubble, Webb, Sphere-X, and more, ready to peel back the coma's glare and constrain the nucleus, grain by grain and line by spectral line. There's a useful humility in the size estimates. If the core were a neat billiard ball, we'd just read its brightness and convert to diameter. But comets are messy, and this one is wrapped in its own exhaust. Hubble's upper limit of 5.6 kilometers is really a not bigger than, with the lower bound set by how bright it must be to show up at all through the haze. The true answer lives somewhere inside that range, and every new observation, every tweak to the dust model, every sharper image chisels the brackets tighter. As for the road it's on, perihelion comes around October the 30th, 2025, at about 1.4 astronomical units from the Sun just inside Mars's orbit, after which the comet will recede, dimming as the engine of sunlight shuts down. The physics is simple, the implications aren't. If 3I Atlas looks chemically familiar, that hints our solar system's recipe cards aren't rare. If it looks alien in key ways, then we've caught a whiff of how differently worlds can assemble, and we'll need to widen our story about planetary kitchens across the Milky Way. For now, the facts we can hold fit in a handful of clear lines, discovered July 1st, 2025 by a NASA-funded sky survey in Chile, confirmed interstellar by its hyperbolic trajectory, safely distant from Earth, bright enough, active enough to reveal itself as a comet, and headed first past Mars where a flotilla of machines will try to catch it in the act. The rest will be written in the way its coma breathes and its tail unfurls as sunlight digs into ice that first froze under a different star. Think of Mars as the balcony seat hanging over the main stage. When 3I Atlas grazes past the red planet, the geometry suddenly tilts in our favour. A nearby world becomes a forward observation post, floating just approximately 0.19 astronomical units off the comet's track, tens of millions of kilometres closer than Earth. That shorter baseline is not just a convenience, it changes what we can measure. With cameras and spectrometers already circling Mars, curious scientists can triangulate the comet's position and motion from two widely separated vantage points, hammering down the orbit and sniffing out any tiny non-gravitational nudges from venting jets that might be too subtle to catch from Earth alone. On October the 3rd, 2025, that geometry peaks. 3I Atlas sweeps by Mars at roughly 18 to 19 million miles, about 29 to 30 million kilometers, barreling along near 193,000 miles per hour. It's a once-per-civilization arrangement, only our third interstellar visitor, and this time we've got assets waiting in exactly the right place. Speed and distance sound abstract until you translate them into what a camera sees. From Mars, the comet's coma and tail fill a bigger fraction of a detector's pixels, which helps separate the bright, fuzzy haze from the starlight behind it. A denser stream of photons means shorter exposure times and less motion blur, crucial when you're imaging an object that appears to slide across the sky faster than many near-Mars asteroids. High-cadence sequences can catch structural changes in the tail, kinks from solar wind shifts, sudden outbursts, or the telltale corkscrew of a jet rotating with the nucleus's spin. Those same rapid sequences let teams search for faint fragments that might shear off as sunlight stresses the surface, the kind of breadcrumb debris that rewrites size and density estimates. With Mars providing the closer viewpoint, even non-detection becomes data. If you don't see fragments above a given brightness, you can bound how cohesive the nucleus must be. Mars doesn't just host a pair of eyes, it hosts a fleet. The European Space Agency has Mars Express and the ExoMars Trace gas orbiter riding high. NASA has Mars Reconnaissance Orbiter, Odyssey and MAVEN, and there are rovers on the ground capable, at least in principle, of sky looks when geometry and operations allow. Each carries instruments tuned to different slices of light. High-Rise on Mar-O resolves fine structure in the coma and inner tail. MARCI and CTX offer context imaging to track broad evolution over hours and days. ESA's NOMAD and ACS spectrometers aboard TGO split light into fingerprints, letting scientists map which gases dominate the outflow. Water vapor here, carbon dioxide there, maybe traces of carbon monoxide or organics, and how those ratios change as sunlight drills deeper into the crust. MAVEN's UV instruments can watch the solar wind's tantrums, buffet the coma and peel off ions, connecting morphology to space weather in near real time. Meanwhile, Mars Express can bring Omega's heritage in near-IR/visible spectroscopy and HRSC's multi-angle imaging to bear, building time-lapse anatomy charts of dust grain sizes and how they scatter sunlight as the phase angle evolves. The result is a layered data set, sharp pictures for structure, spectra for chemistry, and plasma context for the physics that pushes the tail around. Why now? Because interstellar comets don't wait for us. 3I Atlas is still inbound to perihelion at the end of October, which means activity is ramping. Fresh ices are being exposed, jets turn on and off, and the coma is fat with information. Catching it just before peak heating gives us a rare before and after. Mars-side observations near October 3rd to nail the pre-perihelion state. Then follow-ups as the comet rounds the Sun and the balance of gases shifts with temperature. If the water to carbon dioxide ratio changes the way models predict, that supports a familiar formation tail in a chilly outer disk around another star. If it doesn't, if carbon dioxide dominates longer than expected, or if we catch unusual volatiles shimmering in the spectra, then we've learned that planetary kitchens assemble their comets with wider tolerances than ours. With a nearby platform in play, the timing leverages the steepest part of the activity curve where small changes matter most. Mars also buys us sky real estate. From Earth, the comet's angle from the Sun can make observing windows tight. Glare and the atmosphere fight you at dawn and dusk. From orbit around Mars, instruments can point in directions Earth-bound telescopes can't easily sustain, and they can do it without weather and with orbital night/day cycles planned years in advance. That optimizes the all-important phase angle, the Sun-Comet Observer geometry that controls how dust brightens. At certain angles, micron-sized grains light up like glitter. At others, you see deeper into the coma where gas physics, not dust scattering, dominates. By choreographing these angles over a few sols, Mars orbiters can tomography scan the coma, teasing apart layers that would blur together from our planet's line of sight. There's a pragmatic reason for using Mars as a pop-up observatory. It's already there. No launch windows, no cruise time, no fuel margins to negotiate. Just retask existing spacecraft for a compact campaign. Teams upload sequences, rotate a spacecraft a few degrees, tweak exposure scripts and harvest. The cost is mostly planning time and the risk calculus of off-nominal pointing. That's a completely different world from mounting a bespoke flyby mission on a few months' notice, which is essentially impossible. Interstellar visitors don't provide clean lead times. Our best move is to piggyback on the infrastructure we have. And because multiple agencies are involved, we get redundancy. If high-resolution imaging saturates during an outburst, a different camera with a shorter exposures might catch the fine jets. If a spectrometer misses a line because the coma dims, another instrument with a different bandpass might still pick it up. Even when Mars isn't photographing the comet itself, it's a sensor for the environment the comet is flying through. The solar wind at Mars is monitored constantly, its density, speed, and magnetic field direction. Those parameters are the puppeteers that yank a comet's ion tail around. Match tail wiggles with Mars-side space weather logs, and you turn pretty pictures into diagnostics. This twist corresponds to a magnetic sector boundary. That sudden bright knot marks a compression region ramming into freshly ionized gas. Pin those correlations down before perihelion, and you can forecast how the coma will evolve when the heating ramps further. From a purely orbital mechanics standpoint, the Mars pass is our best calibration point. If the nucleus jets are pushing even a little, you'll see it as a deviation from the purely gravitational path. With two baselines, Earth and Mars, you can disentangle real accelerations from measurement noise. That matters for everything downstream, predicting the exact time of perihelion, scheduling deep integrations for big telescopes, and modelling how mass is leaving the nucleus. Because 3I Atlas is an interstellar sample, any constraint on its mass loss rate and rotation state feeds directly into theories of how other planetary systems glue together their dirty snowballs and how easily those snowballs get ejected into interstellar space. the Mars geometry hands you more leverage on those fits in a single weekend than weeks of Earth-only tracking could provide. All of this is happening at a human scale we can feel. A comet forged around a distant sun, seen from the deck of another planet, racing past at airplane per second speeds. The choice of why Mars is baked into physics. The choice of why now is baked into opportunity. The comet is brightest, gassiest, and closest to an instrument-stacked world today, not next month, not next year. When the curtain lifts on a geometry this good, you don't wait, you pivot the cameras, roll the spectra, and let the solar system show you what it looks like when a traveller from elsewhere threads the gap between worlds. First, the feeds slow down. The raw image pages that usually tick upward every hour begin to stall. Social posts get sparse. Outside observers call it a blackout, but inside mission control the word is conjunction. When the sun slides between Earth and Mars, the torrent of radio noise from the solar corona can scramble bits in flight, turning a crisp command into something unpredictable. Rather than risk a garbled instruction reaching a robot 100 million miles away, teams do the boring, sensible thing. They stop sending new commands until the geometry clears. This isn't a one-off quirk, it's a drumbeat baked into the clockwork of the solar system. Roughly every 2 years, Mars and Earth slip into this alignment, and for about 2 weeks engineers impose a command moratorium. The pause isn't superstition, it's physics. Radio waves skimming the sun's atmosphere can be distorted by charged particles, and even with strong error correction, you don't play roulette with opcodes that can move a robotic arm, fire wheels, or pivot a high-gain antenna. So the rule is simple, no commanding during the worst of the alignment. On paper it looks like silence, in practice it's premeditated choreography. Days beforehand, planners stitch together a long homework plan, multi-sol sequences for rovers, multi-orbit sequences for spacecraft, that's uploaded before the sun muscles into the line of sight. The machines keep working. Drive a little, sample the weather, sniff the atmosphere, image a calibration target, log housekeeping. They store what they collect on board. Telemetry usually continues at a reduced cadence, with teams expecting a couple of days of true radio blackout when Mars passes directly behind the solar disk as seen from Earth. The expectation isn't zero data. It's that any data they do receive during the window could have gaps or bit flips, so nothing irreversible is commanded and anything ambiguous gets checked later. From the outside, the dark feeling comes from a few converging effects. First, command uplinks halt, and that alone damps the daily rhythm of new images and status notes. Second, some public galleries of raw images throttle, because the pipelines depend on reliable downlinks and ground processing that's deliberately deprioritized. Third, press updates slow because there's little to say while the robots run their preloaded lists. It's routine enough that NASA announces these quiet periods in advance, date ranges like late August to early September in 2019, or mid-November in 2023, so scientists, educators and space fans know the lull is procedural, not ominous. Under the hood, the Deep Space Network still listens. Goldstone, Madrid and Canberra watch the signal and log what they can. Engineers expect corrupted bits when the radio path passes close to the sun. The team's job is to discriminate noise from truth, flag suspect frames, and set aside anything that can't be verified for post-conjunction re-request. If a packet of images arrives with errors, it gets a "please send again" stamp once the geometry improves. What never happens during the peak is the risky half of the conversation, telling a spacecraft to do something new while knowing the channel is untrustworthy. The robots aren't helpless on their own. Autonomy is part of the design. Rovers and orbiters carry fault protection that watches temperatures, voltages, wheel currents, attitude and more. If something drifts out of bounds during the quiet period, a vehicle can hunker down, switching to a safe configuration, curbing activities, or waiting for ground to reacquire after the sun moves off the path. Teams have lived this cadence many times, and they post-mortem it publicly. Curiosity's operations notes, for instance, describe how the rover followed a long, pre-planned script through the 2023 conjunction and checked in healthy once the blackout ended. Because conjunction is predictable, it becomes a scheduling anchor for science. Instrument teams stack pre- and post-conjunction observations to catch before, after changes in dust, cloud, and atmospheric chemistry. Navigators bookend precise tracking sessions to refine orbits, and everyone plans calibration checks once commanding resumes. Even the Sun gets a turn as the target. Historically, missions have used conjunction to probe the solar corona itself by watching how radio signals at X-band and K-band are delayed and dispersed as they graze the Sun, turning an operational nuisance into a physics experiment. The popular phrase "goes dark" makes it sound like comms vanish everywhere, but it's more selective than that. Most Mars missions suspend uplinks but still downlink health beacons or telemetry at intervals when the Sun probe Earth angle permits, fully expecting some data loss. When the alignment is tightest, there can be a day or two of complete no contact by design. Then, as the angle opens, ground captures trickles of data again, and the mission status pages begin to look alive. None of this is a mystery to the teams. It's annual-ish housekeeping documented with the same straightforward tone you see in NASA's explainers and updates. There's also a human reality to the quiet. Operators shift from tactical execution to strategic prep. While the robots plough through their stored scripts, people write the backlog of plans for the first wake pass, check ground systems, rehearse contingency recoveries, and coordinate DSN allocations for the scrum of spacecraft eager to speak the minute it's safe. The first clean lock after conjunction has a ritual feel: carrier acquired, telemetry frames rolling, health summaries green or yellow, and somewhere in the queue sits that replay request for the packets that skimmed too close to the Sun on the way in. If you're watching from home, the best tell that the lull is procedural is that missions warn you before it happens and then pick up right where they left off. The cadence of images returns, the text updates resume, and the dark window melts into the archive with a tidy label: Solar Conjunction Complete. Mars becomes a balcony above the action, a whole world already ringed with orbiters and sprinkled with rovers, turning itself into a pop-up observatory for a traveller from another sun. The geometry is the gift. When 3i Atlas threads past on October the 3rd at roughly 29 to 30 million kilometres, about 18 million miles, Mars sits far closer to the comet than Earth does, so its cameras and spectrometers get fatter photon streams and cleaner angles through the haze. That proximity, and the simple fact that our hardware is already there, lets mission teams choreograph a rapid multi-instrument campaign without launching anything new. From NASA's side, the workhorses are familiar. Mars Reconnaissance Orbiter can point HiRISE, the half-meter telescope that once photographed a parachuting lander, to go hunting for the bright inner coma and any jets that might betray the nuclear spin. We know it can do this because HiRISE already resolved a comet from Mars orbit during the 2014 Siding Spring flyby, grabbing the first ever resolved images of a long-period comet's nucleus from another planet. CTX can run wide 6-meter per pixel swathes to capture tail structure and evolution, while MARCI and MCS watch the surrounding atmosphere for dust or temperature changes that could complicate the view, or scientifically make it more interesting. The technique is classic: bracket exposure times to avoid saturating the core, interleave short bursts for inner coma detail, with longer integrations for the tail, and repeat on successive orbits to catch any outbursts. Odyssey brings Themis, a visible/thermal imager that proved its worth during Siding Spring by planning thermal IR observations from Mars orbit. A thermal camera is useful here for two reasons. It can tease out large dust grains that stay warm and bright after sunset, and it helps separate faint coma structure from the colder, star-littered background. Themis can also survey the local dust environment in case the comet's passage kicks up changes in the planet skies that might mess with other instruments' lines of sight. MAVEN turns the encounter into plasma theatre. Its imaging ultraviolet spectrograph IUVS can watch how solar ultraviolet light and the solar wind peel ions from the coma and yank the ion tail into kinks and ribbons, then cross-check those wiggles against MAVEN space weather logs. During siding spring, IUVS caught a burst of metallic emissions from a meteor shower flooding Mars' upper atmosphere, even though 3I Atlas is far more distant than that 2014 near miss. Maven's Vantage still turns tail morphology into diagnostics of the environment the comet is flying through. Europe's spacecraft make Mars a true multi-agency observatory. Mars Express can swing HRSC for time-lapse multi-angle imaging of the coma and inner tail, while OMEGA's near-ear eyes look for dust-scattering changes as the Sun-Comet observer angle shifts over a few orbits. ESA's own history book backs the plan. HRSC tracked siding spring across Mars' sky in 2014, demonstrating that the spacecraft can target fast, fuzzy interlopers when the timing is right. Trace Gas Orbiter adds spectroscopy muscle. Nomad and ACS, ultraviolet through infrared, are optimized for sniffing Mars' air, but they can also be commanded to look off-planet. Their band passes span the strongest comet gases, notably H2O, CO2, and CO. By stacking short integrations as the comet slides past, teams can try to tease out faint emission lines against the dark. Meanwhile, KSAS, the colour stereo imager, can acquire high-resolution snapshots to map the coma's brightness profile or catch asymmetries caused by rotating jets. Even routine surface imagers sometimes calibrate on stars and planets. KSAS has documented off-nadir and limb observations before, so a special pointing sequence for a bright comet is within the playbook. On the ground, Martian ground, Perseverance and Curiosity can contribute when geometry and operations allow. Their mast cameras can aim skyward for short, repeated sequences to look for diffuse glow changes at dusk and dawn, or to attempt lucky, long-exposure captures of the comet's brighter regions if the atmosphere cooperates. These systems weren't built to do deep astronomy, but their stability, filter sets, and the habit of routine sky imaging for calibration make them surprisingly handy at recording subtle changes in colour and brightness in the near-horizon sky. If nothing else, rover sky movies help correlate any comet-driven quirks with ordinary Martian weather. What ties all of this together is a coordinated time-box script. The teams target a window bracketing closest approach, run dense imaging and spectroscopy when the comet is highest above each orbiter's horizon, and repeat the same sequences on successive orbits to build a clean time series. Because these are shared assets in a crowded sky, the Deep Space Network schedules and spacecraft power/thermal limits shape the cadence, so plans often include fallback exposure patterns in case a dust cloud, a starfield confusion, or a spacecraft constraint forces a change mid-pass. The playbook borrows heavily from 2014, Get a Sharp Inner Coma Snapshot, HiRISE/HRSC/KSIS. Map the broader coma and tail, CTX/MARCI. Acquire spectra across UV-YMR bands for gas composition and dust properties, NOMAD/ACS/OMEGA/IUVS, and log the solar wind context, MAVEN. Outside Mars' neighbourhood, the relay of observers continues. NASA's own 3I Atlas brief lists a long roster, from Hubble and Webb to Sphere-X, coordinating with Mars assets for a before-after of the comet's chemistry as it brightens toward perihelion on October 30th. That same page confirms the Mars flyby timing and the safe distances involved, which matters for planning long integrations without worrying about hazard operations. The cadence is simple. Catch the comet near Mars when the gases are ramping up, follow the chemistry shift near the Sun, and then keep sampling as it fades outbound toward Jupiter. Even social channels became part of the coordination signal this week, with ESA flagging publicly that Mars Express and the ExoMars Trace Gas Orbiter would train their instruments around October the 3rd. For operations folks, those posts are the tip of a larger iceberg, internal timelines, pointing requests and exposure tables, but they tell you the big thing. Across agencies, the plan is to use Mars like a balcony seat to watch a messenger from another star. Start with the smell of the thing, frozen breath from a world we'll never see. When sunlight begins to gnaw at 3i Atlas, it lifts a halo of gases and dust, the coma, that tells you what the nucleus is made of and how it's put together. In ordinary comets, water vapour is the loudest voice as they warm. With this one, a different ingredient steps to the microphone first. Webb's near-infrared spectra show an atmosphere dominated by carbon dioxide, with water present but way down the bill. The numbers are jaw-tilting. Roughly 8 molecules of CO2 for every one of H2O, among the highest CO2 to water ratios ever measured in a comet, and far off the trend for our homegrown population. Fold in clear signatures of CO, carbonyl sulfide, water ice and dust, and you get a portrait of an object that looks like a comet, but doesn't cook like the ones we know. That imbalance matters because different ices wake up at different distances from a star. Water needs more heat to sublimate. Carbon dioxide can drive vigorous activity farther out. Webb caught 3i Atlas when it was still over 3 astronomical units from the Sun, and the CO2 lines were already roaring. The team's favoured explanation split 2 ways. Either the nucleus is intrinsically rich, meaning it formed where carbon dioxide frost was, abundant near a CO2 ice line in its natal disk, or the surface has a crust that insulates the deeper water ice so effectively that CO2 and CO dominate the early outgassing. Both scenarios encode a different kind of solar system than ours into the comet's chemistry. Independent data back the CO2 story with a striking piece of geometry. NASA's SPHERES mapped an enormous extended carbon dioxide coma around the comet, hundreds of thousands of kilometers across. Think about what that implies. CO2 is not just trickling from a pinhole, it's flooding out, spreading a tenuous sphere that dwarfs the solid heart, and doing so at a distance where many solar system comets are still groggy. An extended CO2 cloud on that scale says hypervolatile engine on, long before perihelion. Dust tells a parallel tale in the way it scatters light. Polarimetry, measuring how light's orientation twists after bouncing off grains, acts like a grain shape detector. Early measurements of 3i Atlas show an unusually deep negative polarization at small phase angles, a fingerprint not commonly seen in comets and asteroids. That points to a peculiar mix of grain sizes, porosities, or surface textures compared with what we've catalogued before, and it contrasts with 2R/Borisov's polarimetric behaviour, which already stood out from the norm. In plain terms, even the dust looks other, not just the gas. Now add the mass clue. When gases jet from a spinning nucleus, they push ever so slightly on the comet, causing a tiny non-gravitational acceleration. For 3i Atlas, careful orbit fits put only a very small upper limit on any such push so far, even as we know the comet is venting strongly. The simplest reading is that the nucleus is hefty and the outgassing roughly symmetric, so the recoil barely nudges the trajectory, consistent with Hubble's constraint that the solid core could be anywhere from a few hundred meters up to a few kilometers across, wrapped in a bright cocoon of dust. Chemistry says hot engine, dynamics say big flywheel, both can be true at once. If you zoom back to the molecular scale, the Webb spectra are a grocery list with personality. CO2 dominates the gas phase. Water shows up alongside it. CO is present at a more familiar proportion, and there's carbonyl sulfide, a sulfur-bearing trace that's been found in solar system comets but not always so plainly. The mixture hints at ices assembled in a cold shadow where carbon compounds were easier to trap, then altered by time and radiation, and then sealed under crusts that crack along sunward fault lines when a new star rises in the sky. Every band in the spectrum is a memory of where and how the comet froze. Spherex's map of the CO2 halo and Webb's chemistry also give modelers leverage on grain physics. CO2, outgassing, tends to loft smaller, lighter dust efficiently. Water vapour can drag bigger chunks when it gets going. If Mars-side cameras and spectrometers see the inner coma sharpen and the colour of scattered light shift as the comet warms, that would dovetail with a transition from a CO2-driven regime to a more water-driven one after perihelion, exactly the kind of before-after experiment this encounter invites. The trick is to catch how the brightness profile and gas ratios evolve as sunlight bites deeper into the crust. There's also the puzzle of why that 8:1 ratio is so extreme. One idea is birthplace. Maybe 3I Atlas formed just beyond its system's CO2 frost line, so the building blocks were inherently CO2 rich. Another is processing. Cosmic rays and ultraviolet photons can erode or rearrange water-rich surfaces over eons, leaving a top layer that releases less H2O when first heated. A third is mechanical, a refractory rind, stone and tar-like material baked onto the surface, can bottle up subsurface water until the heatwave penetrates. Each pathway would produce similar spectra now, but predict different changes later. That's why time series observations across October matter. Meanwhile, the lack, so far, of a strong recoil on the orbit doesn't contradict a furious gas release. It calibrates it. If the nucleus is large and the jets are distributed around the sunlit hemisphere, the vector sum of all those tiny pushes can cancel to below our current sensitivity. As data accumulate, navigators will keep tightening the error bars. If a detectable non-gravitational term emerges, its direction will tell you how the venting is lopsided. If it stays tiny, that reinforces the picture of a massive, relatively symmetric engine. Either way, the chemistry/dynamics duet is the point. The spectrum tells you what is leaving, the trajectory tells you how much oomph it has, and then there's the grain-scale strangeness hinted by the polarization curve. A deeper-than-usual negative branch could mean ultra-fine, fluffy aggregates that flip light in a distinctive way, or compact, glassy grains with surfaces polished by long interstellar exposure. Tie that to the gas mixture, and you can start sketching a life story. A nucleus assembled in a CO2 friendly cold belt, battered by the radiation between the stars, locked under a crust that lets the most eager molecules out first and now peeling open under a new sun, while the dust writes its microbiography in polarized light. The recipe reads simple: CO2, H2O, CO, a dash of sulfur, dust, but the proportions are wrong in all the right ways, and that's exactly what you want from a visitor. A taste of somewhere else that makes your own kitchen feel newly unfamiliar. Start with the hardest part of a comet. You almost never see it. What your camera records is cotton candy, dust and gas, glowing in sunlight and drowning the tiny rocky icy peanut at the centre. For 3I Atlas, Hubble pushed right up against that limit. On July 21st, 2025, it tracked the moving target and measured how the inner glow falls off with the distance from the centre. Then it asked a very specific question. How bright could the nucleus be without revealing itself as a sharp point buried in the fuzz? The answer, after modelling the coma and convolving it with Hubble's point spread function, is that the solid core must be smaller than a circle that would brighten the scene by more than the model allows. Translate the math and you get a nucleus no bigger than about 5.6 kilometers across, and possibly much smaller, down to a few hundred meters, if the coma is doing most of the shining. You can think of Hubble's technique as subtractive sculpture. First, carve a smooth physical model for the near-nucleus haze, how dust density changes with radius, which way radiation pressure sweeps it, how the sunward jet fattens the core. Next, blur that idealized coma to mimic Hubble's optics. Finally, try adding a little unresolved spark at the very center, and keep shrinking it until the synthesized image stops matching the real one. When the fit breaks, you've crossed the upper limit for the nucleus's contribution, and by extension its size, given some reasonable assumptions about how reflective a nucleus is. Hubble's team used the comet standard, a very dark surface, geometric albedo approximately 0.04. Change the albedo and the limit shifts, but not enough to turn a pebble into a mountain. There's a complementary way to play the same game that gives you a lower bound, and it uses chemistry as a yardstick. If you measure how much gas and dust are escaping, you can ask how much sunlit surface area you'd need to power that outflow. Too small a nucleus would simply run out of active real estate. The Hubble analysis makes this explicit. Take plausible drivers, CO, CO2 or H2O, assume they're sublimating from patches on the day side, and calculate what nucleus radius is required so you don't exceed 100% activity. Do that, and the core can't be too tiny. For CO-driven outgassing, the radius must be greater than or equal to 0.16 kilometers, and larger if less volatile ices dominate. With JWST now showing an unusually CO2-rich coma at approximately 3.3 astronomical units, the CO2 or CO can power this branch looks especially relevant, but either way you've got bookends, not smaller than a few hundred meters, not bigger than a few kilometers. One subtlety that matters a lot here is the phase angle, where the Sun, comet and observer sit relative to each other. Dust near the nucleus can forward scatter sunlight and make the inner coma look artificially bright. That's precisely why the Hubble group didn't just do simple aperture photometry. They fitted the profile of brightness with distance and explicitly accounted for a sunward dust plume and an anti-sunward tail shaped by the radiation pressure. If you don't model those pieces, a forward scattering spike can masquerade as a big nucleus. With the profile fitting in place, the coma wins and the nucleus remains hidden, which is how you end up with a robust upper limit instead of a guess. Why not weigh it directly, you might ask? For comets, the closest we come, without a spacecraft flyby, is reading the tiny rocket-like push from outgassing in the orbit itself. If jets shove harder on one side of the rotating nucleus than the other, the path deviates ever so slightly from a purely gravitational track. Astrometrists hunt for that non-gravitational acceleration in months of observations. For 3I Atlas, early fits have found no large deviation. Recent analyses even place a tight upper limit on any such push, meaning the recoil from jets is small enough so far to hide in the noise. That's perfectly consistent with a decently massive, roughly symmetric nucleus, whose outflow isn't lopsided enough to steer its course in a way we can yet detect. Some authors have taken that limit, combined it with JWST's measured gas production and outflow speed, and argue for a hefty lower bound on the mass, pushing the size toward the high end of Hubble's range if you assume comet-like density. But those inferences depend on details. What fraction of the coma's momentum couples to the nucleus? How dust versus gas partition the thrust? That will sharpen only with longer tracking arcs. The gas mix is not just colour commentary, it feeds back into the size brackets. JWST's spectrum shows a coma dominated by carbon dioxide, with water and carbon monoxide present and a sprinkling of carbonyl sulfide, an unusual recipe compared to many homegrown comets at the same distance. CO2 wakes up farther from the Sun than water, which is why 3I Atlas can run a bright coma at 3 to 4 astronomical units. A vigorous CO2-driven engine means you need less sunlit area than if water alone were doing the work, slightly easing the lower limit pressure on the nucleus size. Flip the logic, if the nucleus were too small, even CO2 couldn't sustain the observed coma without implausibly high active fractions. The chemical lever and the brightness lever together wedge the solution into that sub-kilometre to few kilometre window. Rotation and shape usually help too, if you can see the nucleus. A misshapen body tumbles and presents more or less area to the Sun as it spins, modulating the light in a way you can time and invert. But 3I Atlas is already cloaked. Most of the light curve you measure comes from the coma, which damps the nucleus's intrinsic flicker. Even so, some groups using multi-night, multi-telescope photometry report a candidate rotation period near approximately 16 hours, with a small amplitude that's exactly what you'd expect if the dust glow is muting the nucleus signal. That's tantalizing rather than definitive, but if the period holds, it would help constrain how jets sweep around the surface. and therefore how much of the recoil could cancel out over a full spin, another ingredient in the size-mass puzzle. There's also a practical cap on how small the nucleus can be if we don't see certain things. Very tiny, very active nuclei tend to shed fragments or produce narrow dust trails from big, slow grains that have difficulty escaping. Hubble's imaging specifically looked for telltale streaks or clumps aligned with the orbit that would betray prolonged release of large particles. The data show a broad sunward fan and a weaker radiation pressure tail, but no narrow debris trail down to the detection limits. That absence doesn't prove the nucleus is large, yet it removes one of the classic fingerprints of a flyweight, overstressed core. Where can the brackets tighten from here? Better coma suppression and geometry. High-resolution images at different phase angles let you refit the inner profile with a different balance of forward scattering, catch the comet when the dust is a touch less glary, and the same PSF fitting trick bites deeper. Spectroscopy that tracks gas production as sunlight climbs into the subsurface gives you a moving target for the minimum active area calculation, and continued precise astrometry through and after perihelion stretches the time lever on non-gravitational effects. Even a persistent millimeter per second squared scale push becomes measurable with enough clean data. Each of those ticks the error bars inward on both ends of the size window. Taken together, the picture that's emerging is less a single number than a corral, a dark, unresolved nucleus wrapped in a bright CO2-rich shroud, an upper limit of a few kilometers set by how much point source the image can tolerate, a lower limit of a few hundred meters set by the need for enough active real estate to power what we see, and early hints, from rotation candidates and the lack of a debris trail, that the core isn't an ultra-tiny, hyper-fragile speck. That's how you measure the size of something you cannot see. Not by a ruler, but by a web of constraints, optical, chemical, and dynamical, pulled tight from every angle we've got. Start with the scariest line making the rounds. It's heading for us. It isn't. The geometry is boring in exactly the way you want celestial mechanics to be boring. 3I Atlas never comes close to Earth. Its nearest pass to us is around 1.8 astronomical units, roughly 170 million miles, 270 million kilometers, well outside even the Moon's distant neighborhood. If you see, it'll be near Earth in December, translate that to as near as Los Angeles is to New York, multiplied by 700. The only truly close pass in early October is by Mars, and even that close is about 18 to 19 million miles, 29 to 30 million kilometers, which on cosmic scales is politely across the street. Another favourite, NASA went dark, must be hiding something. The quiet you're noticing is the Mars-Solar conjunction routine. Every approximately 2 years, the Sun sits between Earth and Mars, and the hot, ionized soup around the Sun can corrupt radio commands. Mission teams preload long scripts, pause new uplinks for roughly 2 weeks, and let the robots chug through their checklists. That planned hush looks like a blackout from the outside. It's actually the safest way to avoid sending a scrambled instruction to a billion-dollar machine. When the line of sight clears, commanding resumes, and the fire hose of images returns, nothing cloak and dagger about it. If it's so far, why worry about Mars at all? Because science, not safety. We've done this dance before under far hairier conditions. In 2014, comet Siding Spring skimmed a hair's breadth from Mars, about 137,000 kilometers, close enough that agencies briefly tucked orbiters behind the planet for protection, then swung instruments back to watch the show. By contrast, 3I Atlas is tens of millions of kilometers away. No duck under cover, just coordinated observing from a comfortable distance. The difference between hazard ops and bring popcorn is measured in orders of magnitude. Look at that tail, it's pointing at Earth. Tails don't point where comets are going, they point where the sun isn't. Solar radiation and the solar wind push dust and ionized gas away from the sun, so a comet's tails always stream anti-sunward. Depending on perspective, a tail can appear to lean toward or even ahead of the comet's path in a photograph. but that's a trick of projection. If the sun is to the right in the sky, the tails lean left. If the sun is below the horizon, the tails tilt up. That's the only rule they obey. Green equals poison gas, right? Number. The eerie green you sometimes see in comet pictures isn't chlorine or cyanide clouds wafting through space. It's mostly diatomic carbon, C2, in the coma fluorescing in sunlight. C2 shines green, then breaks apart under solar ultraviolet in a day or two, which is why tails typically aren't green, even when the head is. Colour in astro images can be exaggerated by filters, but the physics behind the tint is well understood and not remotely toxic to anyone on Earth. What if it's not a comet at all? Spectra answer that. Observatories reported the textbook fingerprints of a real active comet. Carbon dioxide roaring, water present, carbon monoxide in the mix, even a sulfur-bearing trace called carbonyl sulfide. That's not an engineered exhaust. It's volatile ice sublimating off a dirty snowball. The coma and tail respond to sunlight and the solar wind exactly as comet physics predicts. Exotic headlines come and go. Molecules, lines, and light curves don't care. But it's huge, like city size. Careful with that mental picture. You're seeing the glowing atmosphere around the core, not the core itself. Hubble's best constraints put the solid nucleus somewhere between a few hundred meters and a few kilometers across, hidden inside all that fuzz. That's large enough to be a terrific science target, and small enough to be utterly irrelevant to Earth at the distances involved. If someone waves around Manhattan-sized, they're describing the coma, not the rock ice kernel at the centre. Brightening means it's diving at us. Not necessarily. As 3I Atlas moves inward, sunlight heats its surface, more ice turns to gas, and the comet puffs up, brighter, even if the actual distance to Earth is increasing. Comet brightness is a three-body problem. Distance to the sun drives activity, distance to the observer sets how diluted the light is, and the phase angle, a geometry that can make dust glare or dim. If you watch a live brightness chart spike and assume incoming, you're reading weather as destiny. The weather is solar heating. What about Mars getting sandblasted? At approximately 30 million kilometers, there's no storm of boulders crossing the void. Could microscopic dust from the comet arrive at Mars? Space is full of micrometeoroids all the time, and instruments routinely record that background. The siding spring near Miss was close enough to model and worry about high-speed grains. This pass is so far removed that Mars orbiters are simply pointing cameras and spectrometers, not hiding behind the planet. That's the operational litmus test. I read it might get captured by Jupiter. Hyperbolic means one and done. 3I Atlas is not in a bound solar orbit. Its path is open. Yes, giant planets tug at passing objects, but to turn an interstellar visitor into a long-term captive, you need a very particular, very lossy exchange of energy. The forecasted encounters, distant to Venus, distant to Earth, a few tenths of an AU from Jupiter months from now, aren't that. It will swing around the sun, shed a little mass as vapor and dust, and head back into interstellar space. And the conspiracy wildcard. NASA's silence proves they know it's dangerous. The paradox is that the more dangerous a situation is, the more you hear from mission teams, because hazard operations create constant updates and advisories. The quiet around early October is exactly what the published playbook says it should be. A conjunction pause in uplinks, public notices in advance, routine health beacons when geometry allows, and then a clean return to normal ops. If the goal were to hide, agencies would not publish the dates and reasons years in advance. One last calibration helps everything click into place. If you want a sense of real planetary risk from a comet, look back to 2014, when Siding Spring buzzed Mars so closely that teams actively slewed spacecraft for protection, and still nabbed science, including first ever resolved images of a comet nucleus from Mars orbit. What you see this week looks nothing like that posture. It looks like a choreography of observations from a safe balcony seat, while an object from another sun glides through the spotlight doing exactly what a natural comet should do. What makes this visitor priceless is not spectacle but leverage. For a few short weeks, we can watch an object built around another star breathe as sunlight works its way into the crust, and that time series lets us test almost every part of our comet story. The first lever is the chemistry. JWST has already shown that 3I Atlas is outgassing in a way that's upside down. Compared with many solar system comets at similar distances, carbon dioxide is running the show with water present but far less abundant. The CO2/H2O ratio is about 8:1 in early inbound spectra near a 3.3 astronomical units. That's not a vibe, it's a measurement, and it immediately branches the origin debate. Either the nucleus formed where CO2 frost was abundant, near a CO2 ice line in its birth disk, or a crust is throttling water release so the eager molecules dominate first. Tracking whether the ratios slide toward more water after perihelion is a direct probe of the thermal plumbing. How fast heat penetrates, how thick the rind is, how vents open and shut as the comet rotates. The second lever is scale. SphereX has mapped an enormous extended CO2 coma, hundreds of thousands of kilometers across, long before the comet reached peak heating. That means we're not dealing with a pinhole leak. We're watching a big diffuse engine flood the near nucleus space with gas. With that map in hand, modelers can connect the gas production rate to the minimum active area on the surface and ask a simple question with sharp teeth. How big does the sunlit real estate have to be to power this? If you need more active acreage than a tiny nucleus can supply, you've just shoved the size lower limit upward. If you can power it with modest patches under CO2-driven sublimation, the small nucleus scenarios survive. Repeating those maps before and after perihelion is how you catch the handoff from a CO2-dominated regime toward water, if the handoff happens at all. At the same time, the coma hides the very thing we most want to weigh, the nucleus. Hubble's trick of modelling the inner glow to set a no brighter than this point source limit yields a top-end size around 5.6 kilometers and allows for the possibility that the core is only a few hundred meters across. That's a bracket, not a verdict, and that's the point. The more we refine the coma model, and the brighter fainter balance over different viewing angles, the tighter that bracket gets. If Mars-side imaging sequences can trim the forward scattering glare when the geometry cooperates, the same point spread function fitting bites deeper and the upper limit drops again. Dynamics apply a different ruler altogether. Any comet that vents unevenly gets a tiny rocket push, a non-gravitational acceleration that nudges its path off a perfect gravity-only arc. For 3I Atlas, early fits place a tight upper bound on such a push so far, despite the strong CO2 activity. Keep watching that term through perihelion. If it stays tiny, that implies either a hefty nucleus or outgassing so symmetric that the recoils cancel. If it pops up measurably and points in a stable direction, that vector becomes a clue to where the dominant venting sits on the rotating body. Either outcome is useful because it couples the chemistry to mass and density instead of leaving them in separate boxes. Dust physics is where 3I Atlas already looks intriguingly other. Polarimetric observations, reading how the coma twists the orientation of light, show an unusually deep, narrow negative polarization branch at small phase angles, a combination that doesn't line up with typical comets and even diverges from 2I/Borisov's behavior. That kind of curve usually means the grains differ in size, porosity, or surface texture from the usual suspects. If follow-up observations fill in the missing angles after perihelion and the curve holds, we'll have a micro-physical fingerprint that says something real about how dust was built, processed by radiation in the interstellar space, and released into the coma. Pair that with colour-dependent brightness profiles, and you can watch the grain population shift as the heating wave digs in, another cross-check on where and how this thing was put together. The big picture questions ride on top of those specifics. One track asks about diversity. with Oumuamua, Weird Dynamics, No Visible Coma, 2 I/Borisov, a very comety comet, and now 3I Atlas, a comet, with extreme CO2. What's the spread of materials and structures being ejected from other planetary systems? If CO2-rich objects are common, then the outer belts of other stars may pack their cold zones differently than ours. If 3I Atlas is an outlier, we refine the tails of the distribution instead. Another track asks about ejection physics. Combine the nucleus size/density and spin state with the object's incoming speed and you learn which scattering histories, closed giant planet encounters, long residence in resonant chains, multi-body pinballs, plausibly fling bodies like this into interstellar space. That answers not only what is this one like, but how many more like it should Rubin Observatory and space surveys expect to find per decade, which feeds into future mission designs. Closer to the action, scientists want time-resolved maps of jets and the way they modulate with rotation. Catch a repeating fan or corkscrew in Mars-side image sequences, and you've pinned a spin period without ever seeing the nucleus directly. Align that with spectral changes. CO2 lines brightening when a specific longitude turns into sunlight, and you've sketched a crude weather map of an alien comet. Put a clock on those repeats. Add astrometry precise enough to feel any rocket thrust wobble in the orbit, and you can start solving for active area fractions and even the thermal inertia of the crust. It's a chain. Morphology arrow rotation, arrow jet geometry, arrow recoil, arrow mass constraints. There are also plasma physics hopes that don't sound glamorous but pay off. The ion tail is a windsock. Its kinks and knots trace the solar wind's magnetic field and pressure pulses. With MAVEN at Mars logging the local space weather and remote images showing the tail's instantaneous response, you can turn pretty pictures into a diagnostic tool for how interstellar dust and gas couple to our star's environment, useful every time we try to model a comet's behaviour without being there in person. If the tail responds differently than expected given the measured gas mix, that bounce back tells you something about the charge state and grain sizes in play, which loops back into the dust microphysics story. Spectroscopists will keep hunting for faint lines beyond the big three: H2O, CO2, CO. A detection or tight upper limit on CN, C2, or simple organics would lock down how far the chemistry overlaps with our comet pantry versus how far it strays. Even non-detections can be loud. Stack many exposures from JWST, Mars orbiters, and ground-based telescopes, come up empty for a particular molecule, and you've carved a new boundary on what recipes other disks can bake. Meanwhile, ultraviolet work scheduled on Hubble can probe how sunlight breaks those molecules apart and reassembles them in the coma, a kinetic lab for chemistry that began under a different star. None of this lives in isolation. The NASA overview anchors the calendar, safe distances, a late October perihelion just inside Mars's orbit, and keeps expectations honest about visibility from Earth while the comet is in solar conjunction. That timeline is why the community is pouncing now. You want pre-perihelion CO2 heavy spectra, the Mars-side geometry for sharper morphology and plasma context, and then post-perihelion checks for a chemistry pivot as water wakes up. Stitch those together, and you don't just catalogue a visitor. You test whether our theories of how comets form, crust over and evolve can survive contact with a sample from someone else's kitchen. After it brushes past Mars on October 3rd, the geometry changes again and the clock starts to matter in new ways. The comet dives sunward for a single hot month, with perihelion expected around October 30th at approximately 1.4 astronomical units just inside Mars's orbit, where the extra sunlight will drive the chemistry harder and, if there are crustal weak points, pry them open. That's the phase when jets reorganize, dust grain sizes shift, and any hidden seams in the nucleus announce themselves as brief outbursts. Teams have already paced out their follow-through. Mars assets squeeze what they can from the close pass. Earth-orbiting observatories and JWST retune exposure scripts for the brighter coma, and the deep space missions that happen to be in useful neighbourhoods Like ESA's juice heading for the Jovian system, keep an opportunistic eye on the outbound leg to sample the long baseline evolution while the comet cools. The path is transparent and not dramatic. No approaches to Earth, no last-second swerves. Just a long arc through the inner solar system and back to interstellar space, with October's heat up and the weeks after doing the heavy lifting for science. The cadence is almost musical. Closest pass to Mars, then perihelion, then a distant Earth flyby in December at about 1.8 astronomical units, close in the poetic sense, far in every practical way. The distance keeps us safe and forces a certain kind of discipline. When you can't send a probe to meet a visitor, you turn the whole solar system into a measurement rig. On the inbound side, Mars gives sharper morphology and plasma context. Near perihelion, spectra track where the water finally elbows its way to dominance. Outbound, the coma thins and you can test how fast the vents shut down and which grains hang around longest as sunlight fades. Because the object isn't bound to the sun, there's no second lap. Every window is a one-off, stitched across different platforms and vantage points, and that constraint is why telescope time, DSN passes, and data pipelines are being treated like rocket fuel. Even the far-term choreography has markers. Jupiter's realm is a natural place to keep watching. Not because of any capture fantasy, but because long baselines are priceless for seeing how the dust population evolves when the engine turns down. A spacecraft en route to the Jovian system can log repeat looks months apart, adding a time axis no Earth-based program can match in the same geometry. Meanwhile, Hubble's upper limit game can be replayed at different phase angles as the dust glare changes, chiseling the no bigger than bracket on the nucleus towards something that looks less like a fence and more like a number. Layer in precise astrometry all the way through the outbound leg, and the orbit fitters get their chance to pull a tiny non-gravitational acceleration out of the noise, if it's there at all, and translate it into constraints on mass, active area fraction, and jet geometry. None of those moves require drama. They require patience, scheduled passes, and a tolerance for the way truth arrives as error bars shrinking by millimeters a week. What actually happens inside the data rooms is more tactile than headlines suggest. Brightness profiles get refitted with different dust laws to see which ones are physically sane across October's changing phase angles. Spectral lines are weighed against each other in ratios that act like thermometers and pressure gauges, with time on the x-axis. Does carbon dioxide hang on longer than models for solar system comets would suggest? Does the waterline finally surge after perihelion and stay up, or does it flash and recede like a shallow vent coughing? Tail kinks are matched to solar wind logs to tag which knots were slewed by magnetic sector boundaries and which are genuine outbursts. Negative polarization curves at small phase angles get remeasured to see if that otherness in the dust is persistent or just a trick of geometry. And while all of that runs, schedulers feed the machine. More integrations when the object is high, shorter exposures for their inner coma when it's bright, deeper stacks for faint traces when it begins to fade, a handful of well-placed nights in December when the angle to Earth gives you a clean background for hunting big grains. The road ahead isn't a road, it's a grid of times and angles, and every square you fill changes the picture you'll hang in the archive. Silence is the wrong word for the next stretch. What you're hearing as quiet is a mode switch. When the sun crowds the line between Earth and Mars, teams throttle commanding on purpose because the solar corona can garble bits into something dangerous, and right now, that geometry sits right on top of the Mars window. That planned hush is why social feeds thin out and raw image galleries stop ticking. It's the same play NASA and ESA run every approximately 2 years. The robots don't go dark. They run preloaded scripts, log what they see, and trickle down health beacons when the angle allows. The Deep Space Network keeps listening. Engineers triage what arrives and tag the frames that need a clean resend once the sun moves off the path. To people outside the loop, that looks like secrecy. Inside the loop, it's simply the safe way to not send a scrambled instruction across 100 million miles while the atmosphere of a star is shouting across your channel. There's a different kind of signal in this quiet, the way multiple agencies are using the same geometry like a shared instrument. A Martian orbiter sweeps short exposures in a burst to freeze the inner coma, another stacks longer frames to pull diffuse tail structure out of the dark. Spectrometer slices the light into gas fingerprints. A plasma package logs the solar wind that twisted the tail between frames. Back on Earth, a scheduler flips time on a large telescope because the comet's phase angle hits a sweet spot at an inconvenient hour, and a pipeline engineer raises the memory ceiling on a stacker so faint lines don't get rounded off by the wrong kind of math. If you squint at that for long enough, you can see the outline of the thing that matters most here. Not a single picture or a single spectrum, but the coherence between them. The work is to keep that coherence tight as October tilts to November and the object starts to dim. When the commanding window reopens, the rhythm changes without fanfare. Backlogged packets get replayed. Suspicious frames are requested again. Galleries begin to refill, and the rotation of the comet relative to the Sun has moved on, so the same instruments run the same scripts against a surface that has had weeks more heat. If the water lines have finally risen and the carbon dioxide is giving ground, the origin arguments tilt one way. If CO2 refuses to let go, they tilt another. If the non-gravitational term finally pops out of the orbit fits, navigators hand mass and active area estimates to the people doing the chemistry. If it stays stubbornly small, the hefty symmetric engine picture hardens. And while those lines cross, Mars slides out of its troublesome alignment and the Mars side of the orchestra can play full volume again. The quiet periods also pull focus to the things that don't pause. The star fields the comet slides through, the background galaxies that make good calibration targets, the steady climb and fall of the phase angle that tells dust to glare or behave, the way a tail's edge will sometimes look sharpened like a paper cut because the solar wind decided to be tidy for an hour. Those are the moments instrument teams hoard to test their own assumptions. Did we overfit the inner profile with too much forward scattering? Did we underweight the contribution of larger grains that cool slowly and glow longer? Did we bias the gas lines by stacking on a night when the thermal background drifted? The puzzle is tolerant of ego but allergic to sloppiness, and the only way to keep it honest is to keep adding angles, times, and instruments until the story can't wriggle. There's nothing cinematic about deep time on a server, but it's where the most interesting noises live. A new non-detection that tightens a limit on a faint species by a factor of 2, a sudden bump in the ultraviolet that matches a solar wind kink, Maven logged 2 hours earlier, a colour curve in the dust that steepens after perihelion, in a way that says the big grains are finally dropping out, a rerun of Hubble's nucleus limit that shaves a few hundred metres off the ceiling, because the phase angle cooperated for once. On paper, those look like inchworming numbers. In a script, they look like the thing you get after the news stops being loud and starts being real. Packets arrive, plots update, smear of light becomes a set of constraints, and the next DSN pass is already booked. Somewhere over the red desert, an orbiter blinks, a rover listens to the wind, and a smear of light from another sun slides past the edge of a Martian sky. The public feeds might be quiet, but the instruments aren't. The universe is speaking in photons and timing and tiny bends in a path, and we're learning to hear it. If you felt that hush tonight, the way the noise drops before a concert begins, that's because this is the kind of moment space is made of. Geometry, patience, and nerve. No countdown, no fireworks, just a traveller from far away tugging at our curiosity and our models in equal measure. Over the next weeks, the picture will sharpen. Jets will turn, spectra will tilt, tail lines will kink and unkink with the solar wind. We'll get closer to the heart we can't see by measuring everything around it. That's the game. That's the joy. If you want me to break down the next data burst when it lands, what changed, what didn't, what surprised the people who thought they couldn't be surprised, hit subscribe, ring the bell, and leave me the wildest question you've got about this visitor. I read them all. Until then, keep looking up. The signal is there, even in the quiet.